everybody. Thanks very much for joining us today for this webinar, which is Leaping Forward with Next Gen Robotic Simulation. This is the second webinar of our Next Step webinar series 2021. My name is Phil Glennie, and I'm very proud to be joined here today by Steve Cardoso, the engineering manager at InCycle Automation, and Ethan Tellis, who is a solutions consultant at Siemens Digital Industries Software. I'm going to give you a quick agenda for today. So we're going to start off with some introduction. We're going to say welcome to Next Gen Robotics, and then we're going to look at some success stories, followed by the Q&A. So I'm going to start off here with a little introduction to some digital twinning solutions. As I mentioned, my name is Philip Glennie. I'm the Director of Marketing and Sales at Long-Term Technology Services. So let's start with a little bit about us at Long-Term Technology Services. We are a proud smart partner and technology partner for Siemens Digital Industries Software. And we really want you to think of us as your digital industry partner. So what does that really mean? Well, we're a trusted partner for exploring, those new digital solutions that are going to really help you lower your costs, your lead time, increase your production quality and efficiency, and basically at the end of the day, we're talking about making your company more profitable and a more enjoyable place to work in some cases. So we're going to do this at two levels. First, we've got the more long-term level, if I can use the term, and we're trying to help you build that common digital thread that's running through a number of industry solutions, and these can span from production and design and engineering to production scheduling, plant management, and even sort of machine and line commissioning and robotic programming, which we're going to be looking at today. But we know it's also our mission to meet companies where they are, right? So in other words, if there's anything you see in this webinar that seems like it might be overkill, or just too much upfront investment or time, or in need of internal technical capacity, we just want you to know that those types of barriers, like that's our responsibility to really make those go away and to create situations that work for you. And that means, especially in the mid-market, small companies, mid-market, that means giving you really clear proof of concept, really strong ROI, but just as important, really compressing that payback schedule for you. And we do this through a combination of software, training, and consulting that's really tailored to your exact needs. And we also want to ask you to join us for our next webinar, which is going to be on virtual commissioning, the next step in advanced manufacturing. We'll be joined by InCycle Automation for that one as well. And so today we're going to be talking a bit about how the digital twin can help you reduce your robot programming time by generating your robot code in the virtual world. But this next webinar is going to be more about sort of directly connecting that virtual world with the real world, through either virtual PLCs or real hardware. So that's where you're talking about really driving a simulation with your real PLC in order to validate and generate that PLC code. So as we move on here, here's some things that we're seeing at LTS. So here's some key trends that we are looking at. So as you probably know, there's a number of trends here that are forcing companies to become leaner, smarter, more agile, and doing all of that while somehow increasing the quality of their products. And some of these trends are what you see listed here. So you're talking about customer-driven customization, smart machines, hyperautomation, global competition. Everybody is really feeling these things. And at the end of the day, we're seeing a real explosion of complexity, but the real question is, right, can you deliver more complex things at higher quality in less time? And that's not an easy thing to do. So we believe that the holistic digital twin is really the way to address these challenges. And what we're talking about here, so what do we mean by digital twin? Well, we like to distinguish digital twin from traditional simulation. So if you're thinking of traditional simulation, you're usually thinking about sort of a geometric or a kinematic simulation that's pretty theoretical, pretty hypothetical. It's not the reality. But a digital twin is really a virtual replica of your product or machine that really goes into the realms of things like, electrical engineering, mechatronic, thermal, you name it. It's using physics-based modeling. But what's most important for this webinar is that you can use these to really generate and validate your robotic programming and PLC, which you can then export after validating it in a virtual setting. So now what you're talking about is a type of simulation, a digital twin that really offers a true stand-in for a real object or system, and you can even connect back to that in real time through sensors. And that has really big implications for the way we do things in manufacturing and automation. It's really This approach that allows you to do what we call shifting left. So shifting left, if you think about a timeline, is about bringing more of your manufacturing and your automation concerns and more of that work into the design and engineering stages of your product lifecycle. So you can do this by performing more work than ever before in a virtual setting with total confidence that when it comes time to really manufacture or commission that product, you can do it error-free. So you're not stuck tinkering with a fully assembled machine and production lines, losing time and money in the process while you're tinkering or, in many cases experiencing collisions, interferences that you really have to kind of figure out after the fact. That can all now be done in a virtual setting for much less cost, much less time, and greater accuracy really than ever before. That's really one of the things that has changed and made that type of approach more feasible. So once you've decided that you're going to work with a digital twin, then it becomes a question of, what scope is right for you. Digital twin technology, as you can see here, runs all the way from plant level simulation down to the level of the production line, robotic work cells, robot station. And you can see it runs all the way down to, you're talking virtual PLC and HMI simulation. For the purposes of this webinar, we're going to focus on this second level, the robotic station or the line. In our previous webinar, which we will make available through video, we focused more on the entire plant level. Now we're moving down into that robotic programming at the level of the robotic station or the line. And so with that, I'm very happy to turn things over now to Jeethan Tellis. Jeethan, take it away.
Thank you, Philip. Let me share my screen quickly. I hope you can see my screen now. Thank you. Can you hear me, Philip?
Yep, I can hear you, and I can see your screen now. Yep.
Okay. Let's start with some of the key challenges faced by automation and line builders and also OEM during the project phase. First, we should be able to validate cell components that was designed in any CAD system. Example, the fixtures, jigs, or the other cell components. Going up one level up, when we have different robots based on the customer requirement, we should be able to offline program it and write a specific customer syntax. Typically, it takes a robot-dependent solution provider solution to use it to program a robot, but in our case, we can take it in single platform. Going forward, you should be able to create a path which is free of collision, and the robot should be able to reach all the location in the process. With this, we want to ensure the build quality of our production line. Then we want to go ahead and we want to ensure that we are meeting compliance, cycle time compliance by a customer finally to meet the throughput requirement of the customer. Going further level up, when we have automation components such as safety parameters, control logics, this strategy we want to utilize digital twin and program it, maybe connect a PLC to the digital twin and drive the simulation, test out your code. Finally, we should be able to optimize the space occupied by the cell components in the line. What happens here is it's a complex setup. So in this complex setup, we should be able to find bugs during the design phase itself, download the program directly to hardware, and save some cost during the construction phase. These are must factors to ensure regulatory and customer demands. This is where Siemens OLP and simulation tools comes into picture, which can provide a single platform to validate all these aspects. When we think of robots, we think of cost of hardware is the major investment. Based on the marketing research, it's found that a major chunk of investment goes to robot software and programming. This major cost is spread over the life cycle of the robot. This includes cost of integration all the way up to emergency controls. So how can we reduce this? The solution strategy that we are proposing is to utilize one simulation environment to plan, validate, and all the robotic aspects, such as automation aspect, throughout the entire workflow. Starting right from the simple process definition, ending with a complex virtual commissioning task. Today we will see how you can utilize one simulation platform to simulate robotic cells as well as program it. Extend the scope to modern material handling systems such as AGVs, robot mounted on autonomous vehicle. Use advanced robotics, then we'll extend the scope to use advanced robotics to teach robots directly, which is called hybrid programming. Finally, we will see how we can collaborate in virtual reality world for a smart review. So let me begin with the first, robotics and mechanical motion planning. To build a digital twin of your cell or line, you can import data from multi-CAD system, example, a SolidWorks. Now you bring in CAD data. Also, you can bring in robot models from the library. It could be from multiple vendors. We bring in that and we start building the robotic cell. Once we build the robotic cell, we want to be able to create a path which is collision free. With a few clicks of button, now you can offline program the robot once the path is defined. Once the offline program is ready, we can download it with a specific robot syntax. For example, Fanuc has its own syntax. You can download in specific file format. We support, as I said, all major industrial robots, just to name a few, ABB, KUKA, and list goes on. So in this example, we are going to see a robotic, first we are going to see a robot collision detection with the cell components and how to avoid that. Second, we'll see robot path creation. Finally, we'll see how easy it is to create offline program in Process Simulate environment. Let me go ahead and play the video. During the robotic path creation phase, collision detection is a crucial aspect. Process Simulate helps you dynamically detect collision during the robot simulation and motion planning phase itself, providing shop floor workers safety and preventing costly damages to the equipment. In one of the customer case, the robot collided with the equipment, which resulted in loss of production time. Using the collision detection mechanism, now you can carefully analyze where the penetration is, whether it is a near miss collision, whether it is a through collision penetration, or it's just a contact collision, as you can see on the screen. At this point, we want to avoid the collision. We can dynamically add a robotic location or modify existing one in easy way. You can dynamically drag, drop, interactively play with the robot cursor. At this point, you can copy paste a location and drag and drop it. Change the location position within the sequence and rename the location and more. Then we simulate the updated path to verify changes have taken effect. You can simulate the entire process sequence in a single shot. At this point, we can go ahead and create OLP program. Further, we can change the motion parameters, such as here, for example, from point to point to linear motion type and the speed of that location. Once the OLP program is done, the program with the specific robot syntax can be directly loaded into a robot. This gives major advantage over the online programming method or teach-pendant programming method. So just to summarize, using our solution, you can create robotic path free of collision with the ease. Perform robot in offline mode with the robot specific syntax to save time and money. Optimize path to achieve lower cycle time. Next, we'll see AGV and robot mounted on the AGV case. Typical material transport equipment used in plants and warehouses is quickly being replaced by automated and smart systems. AGVs are leading the transformation. Our solution provides one platform to create AGV paths, avoid obstacles, and finally virtually commission an AGV fleet. Let's see an example. In this real life example, you can see how we can simulate AGV paths, interaction of AGV with the augmented automated system, and finally we'll see how Process Simulate as a potential test bed for testing entire fleet of AGVs. Let me go ahead and play the video. AGVs are more and more frequently adopted at warehouse and logistics. You can analyze throughput of system with multiple AGVs and validate AGV behavior, combine AGVs and industrial robots together. At this point, we can see AGV interacting with the robot. You can take advantage of PS to validate AGV's path selection, how it interacts with the other automation assets. When PS is connected to external AGV fleet management system, its virtual commissioning functionality would allow PS to become a virtual test bed. At this point, you can see AGV is interacting. You can see where there's a collision or not. Basically, AGV is interacting with the cell components. Once we have fleet management solution connected to virtual commissioning, we have a direct communication between them. We can detect the human, for example, here, and commission entire AGV fleet. This will allow us to minimize the risk and cost of commissioning. Using digital twin, in simulation environment, we are able to simulate detailed AGV parameters such as AGV control, path, and fleet management strategy. Let's see our next example, a hybrid teaching technique. Here, what we are going to use is a universal robot, leveraging digital twin of a cell, and a robot to validate entire manufacturing process. PS can connect to a universal robot to replicate movement of digital twin. Let me go ahead and show you how we can utilize hybrid environment using a real hardware or real manipulator and a digital twin in Process Simulate. In this example of universal robot, we will see hardware interaction on online programming. It's an online programming. Digital twin motion update in real time. Real robot interaction with the virtual cell. Let me go ahead and play the video. Collaborative robots are being deployed to factories, especially for the scenarios that robots are working with a human being. One of the most successful cobots is universal robots, which Process Simulate already offers offline programming support. PS now extends its offering to leverage the hardware interactive online programming functions. With this, now you can have only few steps to make a real-time connection between PS and simulation environment. Use real UR robot or universal robot via Ethernet cable. Once the connection is established, you can drag and drop objects directly. Use the teach pendant of the robot, and the same thing is being reflected in the digital environment, as you can see. Now the advantage or the beauty here is that we need not have all the cell component. We can interact directly with the robot in physical environment, but it will also be translated into a digital environment in real time. This will save us a time in terms of building the entire facility. One second, we can have single robot to program multiple robots. What I mean to say is that with a single robot, you can use it to program maybe 20 or 30 universal robots, which are working, collaborative robots, which are working in the line. Hybrid programming allows us really to interact with the physical robot as well as a digital twin of the cell. This will reduce the programming time. Also, this will allow this will allow us to interact with the cell environment without any collision. Let me go to next slide. Once the digital twin of your cell or line is ready, you can take this data into a virtual reality environment wherein you can immerse yourself and walk through the digital twin, see where the problems are happening. Once you detect those problems, you can take the note and pass it back to your design department, or customer can comment on the issues and you can take that notes and work on it. Let's see an example. In this example, what we are going to see is how you can take a cell data into virtual reality environment, and then how you can walk through in digital environment, finally, how to create a notes when you detect some issues or when you find out some issues. Let me go ahead and play. Once a process simulate study is finished, you can load that study into a virtual reality environment. Once the study is loaded, you can start to navigate inside the cell. We call it as a teleport, wherein you can move yourself from one point to other point with the ease. We support HTC Vive system for our virtual reality application. One can start the simulation, manipulate a robot using torch light to see dark areas. We can literally go on the cell, we can literally go on the robot, which is not possible in real life, which may result in collision. If we want to navigate, we can play the simulation at this point. We can navigate to different areas. We can interact with the cell component. For example, here we are moving a robot from one point to other point to see, to check the feasibility where it can fit well. Once we have that, we can navigate to other areas, go inside for example, in this example, we can go inside the car or under the car. Whenever there is if the area is dark, we can switch on the light and we can see in detail what's exactly happening in the digital twin, which is not possible with the real interaction or a real production shop floor. At this point, we can navigate to a different point. We can use different options. We detect an issue at this point. You notice some issues that are happening in the cell. Now we want to create a note and send it to a designer as well as to a simulation engineer. We can quickly highlight that area, take a snapshot, and send it to a designer for editing as well as for simulation engineer to revalidate. We can interactively play with the simulation. It's not a static, it's a dynamic simulation here. We can see robots moving, we can see detailed welding process. And really we can immerse ourselves inside the environment. If there's a collision, we can detect the collision. We can teleport inside the car, like how we are driving. We can see in different angles how the cell components are interacting with the part, or in this case, a car. Here you can see in detail the welding process, spot welding process, and riveting process. Use virtual reality environment as a smart review tool for internal and customer review, which will translate to reduction in cost and which will also translate in avoiding the unnecessary travel. With that, in a nutshell, what we have seen is a robotic application supported by our solution, not just to meet your current requirement, it is also geared towards addressing future scenarios such as autonomous robots, AGVs, and collaborative robots, to name a few. Finally, we have seen how we can collaborate in virtual world for a smart review when our review is due. With that, I will hand it over back to Philip.